In this video, we're going to start chapter 5 of the trigonometry textbook. Chapter 5 is on trig identities, trigonometric identities. And so you might already be familiar with a sheet of paper like shown here. You can Google this, go to Google Images, and there's all kinds of different ways that the trig identities are laid out like this. If you're not familiar with something like this, then you'll be using this a lot as you go through school, not just in more advanced math classes like calculus, etc., but even for like engineers, you'll be using the trig identities in all kinds of different situations. And so what we're going to do in this chapter is look at the details of how all of these equations here are derived. And then we're going to practice manipulating equations in different scenarios using the trig identities so we can become more familiar with them. Now, you might remember in chapter 1, we actually already went through some of these. These first 3 here, we've actually already talked about. We went through the whole derivation of these, right? The Pythagorean identities, if you go back to the beginning of the playlist at the end of chapter 1, there's a dedicated video on each one of these identities. Okay, this was at the end of chapter 1. We talked about the reciprocal identities, Pythagorean identities, and the quotient identities. Now, in chapter 2, we did look at what was called cofunctions, and that's actually going to be an identity that's going to be on the list. However, we didn't look at the full scope of cofunctions in chapter 2, and so we're going to bring we're going to bring this full circle in this chapter, in chapter 5. Okay, and so the goal for this chapter is, again, we want to see exactly how all of these identities here are derived, but then it's more than just that. We want to work example problems where we get a lot of practice in different scenarios manipulating these and working with these. And you might say, well, why do we need to do that? Well, because it's going to help you, it's going to help cement all of this in your brain better. It's going to help you retain all of this better, become more intimately familiar with it. Okay, so seeing in detail how they're derived and then working an array of example problems using these is going to make you a lot more comfortable with a trig identities sheet in the future. And not just with the trig identities sheet, but in a scenario where you see something in calculus or in engineering or whatever, and it'll come to you quicker that, hey, I could use a trig identity here, because you'll have a lot more experience working with them, as opposed to if you're just kind of told what these are and you see the sheet and you see the identities and you know they exist, but then when it comes time to actually potentially apply them in a situation, you completely forget about it, right? Okay, so now let's take a look at the opening section, which talks about the fundamental identities. All right, here's this opening picture of chapter 5. It says electricity that passes through wires to homes and businesses alternates its direction on those wires and is modeled by sine and cosine functions. So I don't know what that has to do with trig identities. It's just telling you an application of sine and cosine functions. But yeah, I mean, you can use, there's going to be all kinds of applications of trig identities as you go through school. Okay, so here's the fundamental identities. And so included with these are the reciprocal identities, the quotient identities, and the Pythagorean identities, which if you want to go look at where these come from, go back to the videos at the beginning of the playlist. But also included are the even-odd identities, and we haven't talked about those officially yet, and that's what we're going to talk about here. All right. Recall that a function is even if f of minus x is equal to f of x for all x in the domain of f, and a function is odd if f of minus x is equal to minus f of x for all x in the domain of f, right? That's what an even and odd function means. And we saw in the previous section, we saw that tangent and cotangent are odd, secant was even, and cosecant was odd. And then what was it? It was cosine was even and sine was odd. Yeah, sine would be odd, I want to say. Yeah, sine was odd. Okay, we have used graphs to classify the trigonometric functions as even or odd. We can also use figure 1 to do this. Okay, so yeah, we use the graphs to classify them as even or odd, but they want to use this graph. So as suggested by the circle in figure 1, an angle theta having the point xy on its terminal side has a corresponding angle minus theta with point x minus y on its terminal side. Okay, so what is this saying? An angle theta having point xy on its terminal side. So like here's angle theta with the terminal side, point xy. You could pick any point on the terminal side, right? But we're thinking about a circle of radius r that we're putting the points on. Has a corresponding angle minus theta with the point x minus, oh, okay. It's not on this minus theta is not on the same terminal side, it's on another terminal side, okay? From the definition of sine, we see that sine of minus theta and sine theta are negatives of each other. Yeah, so we're using the general definition of trig functions here. You could use any circle if you wanted to use a circle. It didn't have to be a unit circle. And so sine theta here is this minus y divided by r. Sine of this theta is y divided by r. Okay? So, yeah, that sine of minus theta and sine theta are negatives of each other. Sine of minus theta. Yeah, so it's just another way of looking at the fact that sine is an odd function. Sine of minus theta is equal to minus sine theta for any theta. No matter what, it's any theta. And yeah, we talked about this in chapter 1, but it says this is an example of an identity, an equation that is satisfied by every value in the domain of its variable. So yeah, this term identity, this should sound familiar to you. This is from algebra, right? What was an identity in algebra? An identity was so we were learning how to solve equations in one variable. So we had an equation with like an x on both sides or whatever, and we went through the process of adding to both sides, subtracting from both sides, multiplying both sides, whatnot. And then in the end, the variable disappeared, and you were left with, this could happen. This didn't happen every time. Usually you got like x is equal to something, but there were special cases where you simplify, the x disappears and you have something like 0 is equal to 5. Well, that's not true, so that's a contradiction. That you called that a contradiction, so that meant that there's no solution to the equation. There's no x you could plug into the equation and satisfy the equation. But there was a third scenario where you got something like maybe 5 is equal to 5, and you could subtract 5 from both sides. So really you always got like technically 0 is equal to 0. Well, we called this an identity. And what that meant was that any x you plugged in, x was restricted to real numbers, any real number within the domain, which most of the time was all real numbers, the equation was satisfied. And that's why these are called trig identities, because you can plug in any value of theta within the domain of theta. So that's like, theta goes from negative infinity to infinity unless it's involving one of the trig functions that with a quadrantal angle that you can't put in, right? Like cotangent of 0 is undefined. But like any other theta, as long as there's no domain issue, the equation is satisfied. There's not one unique value of the variable that solves the equation. All values of the variable within the domain solve the equation. And so that's why these are called identities. An identity is an equation that is satisfied by every value in the domain of its variable. Okay, some examples from algebra are, so this is an identity because you simplify it and you could reduce this down to 0 is equal to 0. Now, you might be thinking, well, but identities were they weren't of much use, right? If we had an identity, it was like we couldn't solve for x. Well, yeah, but what they're illustrating here, though, is like this is useful in the sense of, so, okay, this was the difference of two squares formula, right? X squared minus y squared, you could write like this. X plus y squared, so the perfect square trinomial is shown here. So that's the usefulness of them. It allows you to, you can put things in different forms. You can relate things together that are equal. Right? If you ever see x squared, something squared minus something squared, you can put it into this form. That's what this identity tells you. So it's not about solving for unknowns as it is more of identities are allowing you to change forms, to manipulate equations, simplify equations, etc. Okay, figure 1 shows an angle theta in quadrant 2. So yeah, this angle's in quadrant 2, but the same result holds for theta in any quadrant. The figure also suggests the following identity for cosine. Yeah, so this is, we know that from the fact that it's an odd sine's an odd function that this holds for any theta, but this setup here is general as well. This proves it from another, not from a graphical method, not from the graph of the function method, but from the trig function definition perspective. This proves it for all theta. Okay, now, yeah, so, but we know cosine's an even function, so here's another identity. So yeah, what they're saying is we're going to state this as a trig identity, right? We're going to put this in the list. Here's another relation between trig functions. And then here's another trig identity. We're going to use the fact that cosine is even, sine is odd, tangent is odd to make more trig identities that we're going to put in the list. Okay, and then you could do, we know that, what was it? Secant was even, cosecant was odd, cotangent was odd. So we're going to put all of those in the list of trig identities. These are called the even-odd identities, just from the fact that if they're even or odd functions. All of the trig functions have a symmetry, an even or an odd symmetry. Okay, so these even-odd identities together with the reciprocal, quotient, and Pythagorean identities make up the fundamental identities. So it's something to note. These are the fundamental identities. Note, in trigonometric identities, theta can represent an angle in degrees or radians or a real number. So when they say real number, they're talking about like the circular functions. But yeah, so why is this true? If this confuses you, think about why this is true. The reason why it doesn't matter if it's degrees or radians or whatever is because the definition of trig functions, okay, is based on an angle, theta, right? If you have an angle theta, then you can you can have trig functions. You can evaluate trig functions with that angle. Well, this is just units, right? It doesn't matter what units you use for the angle. You can use whatever units you want. It's okay. Whatever the units are, what does that angle represent as far as the definition of angle? It's the amount of rotation from, like, we have two rays with a common vertex, and then you've rotated one ray with respect to the other. It's straight side rays. How much is that opening, right? So it doesn't matter what units you use, as long as you understand the amount of opening you're talking about in terms of angle. Well, then you come to the definition, put it in here, right? And we know, like, sine of that angle is y over r, etc. So it doesn't matter what the units are. Now, no, you can't say, okay, like on one side of this identity, we're working in radians, and on the other side, we're in the theta's in degrees. Well, no. They're saying that you can, kind of like in a box, right? In one scenario where you're working with a trig identity, in one scenario, you can say, okay, the theta is in degrees for all the work I'm doing here, or it's in radians for all the work I'm doing here. You can do that, or it's in radians or gradians, whatever. You can't like mix them in, because then you're not dealing with the same angle. I mean, you could mix them in, but then you have to convert to make sure you're dealing with the same amount of opening between two straight sides. Okay. So there's the even odd identities added to the list. Okay, now it notes here that with the Pythagorean identities that we might see the Pythagorean identities in different forms. Right, you could write sine squared theta as 1 minus cosine squared theta, but that's not its own unique Pythagorean identity. That comes from this. Okay, so that's the fundamental identities. Now it says, okay, we can use these identities to find the values of other trigonometric functions from the value of a given trigonometric function. So yeah, we're going to work example problems, and this might seem trivial, but I would really focus on these because it's going to be good practice. It's going to be good repetition for you to retain these identities. So, all right, if we know that tangent theta is minus 5/3, and then we know that theta is in quadrant 2, then find each function value. So let's find secant sine of that same angle. Okay, now, we could technically do the inverse of this. We haven't officially learned inverses yet, but we know how to use our calculator to do an inverse, get the angle that way. But no, we want to use trig identities, one of the fundamental identities to get these values. So, okay, well, the first thing I think about is, well, what about the reciprocal of this? So 1 over cotangent theta is tangent theta, so cotangent theta is minus 3/5. Okay, but do they ask us about cotangent? Well, here's cotangent. They want cotangent minus theta. Well, okay, what's the cotangent is what? That was odd. Yeah, so cotangent minus theta is equal to minus cotangent theta. And then cotangent theta is minus 3/5. So this is going to be 3/5. All right, well, that's an easy one. Okay, now, so tangent, then I think, all right, tangent sine over cosine. So we can get like sine theta is equal to minus 5/3 cosine theta. Okay, maybe we could use that. But let's see what they do here. They use there's a relation, the Pythagorean identities, there's a relation between tangent and secant. And we have tangent, and we're looking for secant here, so yeah, there we go. So they use this Pythagorean identity, plug tangent theta into here, and simplify and get 34 over 9 is equal to secant squared theta. But then you take the square root of both sides, you have to put a plus or minus. And so now, there's two possible values. And so that would be we have to just state, well, it's one of these values, and that would be the answer unless we have more information. Well, they give us more information. They say that theta is in quadrant 2. So in quadrant 2, if we think about secant, quadrant 2, so secant is the reciprocal of cosine, so that's r over x. Well, x is negative in quadrant 2, so secant, and r is always positive, so secant's going to be negative. So we know it's going to be not the positive, but the negative. So we choose the negative, and there's secant theta. They rationalize it, or they didn't need to rationalize it. That's it. Minus root 34 over 3. All right, now sine, let's see. So tangent theta is sine over cosine. So sine theta is equal to minus 5/3 cosine theta. Okay. Now, all right. Well, we have secant and tangent, so we could use either one of these, and we actually have this cotangent of theta as well if we want it. But they're probably not going to have us use this because this actually came third. So, yeah, we have secant. Secant is the reciprocal of cosine. So, okay, we could divide both sides of this by cosine. And what we get is secant theta sine theta is equal to minus 5/3. So sine theta is equal to minus 5/3 over secant theta. So that's going to be, let's see, the minuses will go away, and you've got, it's minus 5/3 times minus 3 over root 34. So 5 over root 34, which is 5 root 34 over 34. And yeah, there you go. But again, we could have potentially used, so cotangent of minus theta is 3/5, but cotangent of minus theta is equal to minus cotangent theta. So minus cotangent theta is equal to 3/5. So cotangent theta is equal to minus 3/5. We could have used this too. All right. When taking the square root, be sure to choose the sign based on the quadrant of theta and the function being evaluated. Yeah, so if you take the square root of both sides, you have to put plus or minus. And let's say you don't have information to decide on which to choose. Well, then your answer is it could be either one of these, right? But typically for these types of problems, the problem statement will give you the additional information you need to choose which sign to take from the square root. All right, writing one trigonometric function in terms of another. So write cosine x in terms of tangent x. How can we do that? So what they're saying is we want cosine x by itself is equal to some expression that just has tangent in it. Okay? So what they do is they use this Pythagorean identity, and the reason is because we have a secant here, and we know that the reciprocal of secant is cosine, and then there's a tangent on this side. So you get, they take the reciprocal of both sides, and this becomes cosine squared x is equal to this. Take the square root of both sides, plus or minus, and then they can apply they kind of simplify, they put the square root, they simplified it a little bit with the square root up here, just putting this as plus or minus 1 and putting the square root down here. And then they rationalize and get this. You can put that plus or minus wherever you want, because the 1 plus tangent squared of x, that's always going to be positive. You know, it's a principal root, so it's always positive coming out of a principal root, but you know, even the stuff inside, it's something squared plus 1, so even there's no chance that the argument is going to be negative either, but that doesn't matter because you can't have a negative come out of a principal root, so you can just put the plus or minus wherever you want. And the choice of the positive sign or the negative sign depends on the quadrant of x. And the way you look at it is cosine can be positive or negative, right? We know all the trig functions can be positive or negative, so it makes sense that in complete general, if you're expressing cosine or any trig function as a function of another trig function, it's going to have a plus or minus in it. And if you're doing it in complete general, because all the trig functions can be either positive or negative, so there's two potential values. Now you might be thinking, well, wait a minute, this isn't a function though, right? You have one input is corresponding to multiple outputs. No, this is deceiving. This is a case where you input an x, and then that's going to dictate. You're going to know which one to choose. You're going to eliminate one. It's not going to. There's no x you can input, and you're going to keep both the plus and the minus. So no, this is still a function. This is the cosine function expressed in terms of tangent. All right. The functions tangent theta, cotangent theta, secant theta, and cosecant theta can easily be expressed in terms of sine, cosine, or both. Yeah, so it makes sense that you can express tangent as a function of just sine, cotangent as a function of just sine or cosine, or like a mixture of both, whatever. So they give an example here. If you had 1 plus cotangent squared theta over 1 minus cosecant squared theta, could we switch this to being just a function of sine and cosine and eliminate the cotangent and cosecant, and then simplify it as much as possible? Well, okay, we know that cotangent is, with the quotient identity, we can write that as cosine over sine. So if we're trying to get to cosine and sine, then absolutely make that substitution. So that's what they do here. And then cosecant with the reciprocal identity for it, that's going to be 1 over sine, do that as well, right? So now there we go. We're just in terms of cosine and sine, but they want to simplify it, so they multiply by 1 in the form of sine squared over sine squared and get rid of the fractions. And then we're left with sine squared plus cosine squared in the numerator. That's just 1. And then sine squared theta minus 1, if you rearrange, this is a Pythagorean identity rearranged, that's minus cosine squared theta. And, well, why would they do this? Didn't the question say to write this in terms of just sine theta and cosine theta? Or one of those, or either just one of those or both or whatever? So why did they go to secant? So, I mean, to me, I guess according to the question, this is the final answer. But, you know, whatever. Okay. Now, caution when working with trigonometric expressions and identities, be sure to write the argument of the function. For example, we would not write sine squared plus cosine squared is equal to 1. An argument such as theta is necessary to write this correctly. Yeah, so, you know, it's easy to say when you're just talking, you know, I've probably done this throughout the video as we've gone along and throughout this whole course. You just say sine plus cosine, or sine squared plus cosine squared, etc. You don't say what the argument is, sine squared of x or cosine squared of x or sine of alpha, cotangent of alpha. But, when you're writing it, though, you can do that in speech just for convenience, right? But when you're writing it, though, this makes no sense, because a tangent function it's of an angle. It would be like saying, what is the square root times the logarithm, right? What is, simplify this? Well, this doesn't make any sense, right? You have to, these are just operators. You have to operate on something. And it's the same idea with trig functions. Those are operators. You have to operate on a variable. You can't say the cube root times the fourth root. This doesn't make any sense, right? How could you can't write this in variable form? I mean, so you have to put an argument. Okay, so now let's work some example problems, and this is going to be good practice, good repetition to really ingrain all this stuff into your brain. So, okay,